The title of the thesis is Regression, Absorbing Acoustic Metasurfaces, Deep Learning Approach and Experimental Demonstration. Let me first introduce the jury. So I'll begin with Abdelkrim Khedif, who is online. Yeah. So from Université de France, Franche-Comté. Jan Penet from the University of Lille. Agnès Morel from ESPSI de Paris. Jean-François Cambofer from the University of Lorraine. Badreddin Asouar from your institute, Mahmoud, and I'm from Nico de Klerk, I'm from the Georgia Institute of Technology. So we are a little bit late, which means I will give the So you have around 45 minutes to explain everything, and then you will ask questions.
Okay. It's okay, I know. Thank you, Professor, for the introduction, and I welcome you all for my PhD thesis defense. Our one jury member is attending online, so I will prefer to speak from here so we can see and look each other. So today I will present my PhD dissertation work that is on the topic low frequency absorbing acoustic metasurface, deep learning approach and experimental demonstration. This presentation will be followed in this manner. It is divided into 5 sections. First, I will talk about context and state of the art, then objective of this thesis. In the first part of this project, we designed the multi-coiled metasurface that I will discuss in second section. In third section, I will talk about artificial neural network in brief and how it can be implemented for the acoustic metasurface absorbers. And in the fourth section, I will talk about forward and inverse designs for omnidirectional incidents. And finally, we'll conclude the work and we'll talk about the future perspective. We all know that noise pollution has become an integral part of our daily lives, and more specifically the low frequency noise, which has adverse impact on our health and quality of the life. For this reason, World Health Organization has also considered the noise as a crucial factor that affects our health and quality of the life. And time to time, it provides the guideline to control this low frequency noise. Now, the major sources of these low frequency noises are first transportation. This is mainly concerning to the big cities. Then another sources are industrial machineries, wind turbine and amplified music. Now, regarding its effect on our health, first it has great potential to create the annoyance. The prevalence of this annoyance increase with the high sound pressure level. And another effect, it may create a lack of concentration and sleep disturbance. And also some studies has observed its long-time serious effect on our health. For example, in a Danish study, they find the evidence that long-term road traffic noise leads to the cardiovascular disease. So for all this perspective, it is essential to find some efficient means to control this low frequency noise. Conventionally, various types of absorbers based on porous and fibrous material, gradient index material and microperforated plates are used. However, these absorbers are either bulky or structurally weak. And its dimensions are also comparable to the working wavelength. So it is not practical to implement them for the low frequency applications. Since last 2 decades, the introduction of acoustic metasurface has replaced all the conventional means to manipulate the sound, and it also includes the application for attenuation and absorption of the sound that we will see in the next slides. So acoustic metasurface is based on the generalized Snell's law. They are 2D materials with subwavelength thickness that is capable to provide non-trivial local phase shift. The concept of the acoustic metasurface is based on this subwavelength unit cell, It usually includes this type Helmholtz resonator, then coiling up space channel, and membrane type of metasurface. Using this kind of structures, various functionalities like reflection, transmission, and absorption of sound can be achieved. Now, regarding the application of acoustic metasurface for the low frequency absorption, there is extensive literature available, but here I will talk only about main three approaches. So first is based on the hybrid resonance. So here is membrane type of metasurface that consists of a membrane, a solid reflecting surface, and platelet. Here the solid reflecting surface and sealed gas provides the extra impedance in the series that change the resonance condition. And using this structure, nearly perfect absorption was achieved at 152 Hz with the total thickness of the structure 17 mm, that is lambda by 133 in terms of the working wavelength. Another approach is based on the slow sound and critical coupling. So here is the thin panel that consists of a closed slit cavity, and upper part of these cavities are loaded with the Helmholtz resonator, which helps to slow down the sound. And using this structure, perfect absorption was achieved at 338.5 Hz with thickness of the panel 1.1 cm. One more approach is based on the coiling up space structure, which was proposed by our group in 2016. So here is the structure. It consists of two parts. First, perforated plate and a coiling channel in the back. This structure is designed to achieve full absorption by satisfying two conditions. First, the resonance state, and the second is impedance matching with the surrounding medium. So when these two conditions are fulfilled, all the acoustic energy absorbed within the coiling channel and without reflecting back. Using this structure, perfect absorption was achieved at 125.8 Hz with the thickness of the structure 12.2 mm, which is just lambda by 223 of the working wavelength. So as an extension of this work, the main objective of this Ph.D. dissertation is to design ultra-thin acoustic absorber for extreme low frequency below 100 Hz. Till the date, for the absorber designs, we either use the theoretical approach or based on the numerical simulations. The numerical simulations are based on the finite element method, and what we do here, first we build geometry, then we put some initial condition, then we set some boundary condition, and then using Navier-Stokes equation we can calculate the acoustic response. Using sufficient number of mesh and sufficient number of iteration, we can generate accurate acoustic response using this approach. This approach is good when the structure is simple or we have low degree of freedom. But as the structure becomes complex or degree of freedom increases, it is difficult to explore the whole design space using this approach due to time and computation power constraint. For this problem, we identify the solution by implementing the modern deep learning architectures. To achieve these objectives, in first part of this dissertation, we implement ultra-thin metasurface absorber based on the multi-coil structure to achieve the extreme low frequency absorption. In the second part, we implement deep learning driven metasurface absorber designs. So we use convolution type neural network for the forward design, and for the inverse design, we use conditional type generative adversarial network. So now moving to the first part of the result, multi-coil metasurface absorber. As I mentioned before, the coiling up structure concept was proposed by our group. So as an extension of that work and to achieve the absorption below 100 Hz, we studied several kind of geometries and we finally end up with this multi-coiled metasurface structure. So this structure consists of three parts: perforated plate, circular aperture and labyrinth structure. Here, the circular aperture adds extra degree of freedom to tune the impedance, which helps to shift the resonance toward lower frequency up to certain limit. Then we introduce total 11th labyrinth structure inside the coiling channel. Here, the labyrinth structures allows to shift the resonance towards the extreme low frequency. So there are two benefits of this geometry. First, it fully utilizes the space inside the coiling channel, and the second is that it weakens the dependence of resonance on the propagation channel length. To study it theoretically, we used lumped RLC circuit model. So here, aperture, perforated plate and labyrinth structure contributes to acoustic resistance and inductance, and the cavity. Cavity is the area between these two labyrinth structure that provides the acoustic capacitance. So by solving this circuit and calculating its impedance and putting its value in acoustic absorption equation, we can generate the acoustic coefficient spectra for given frequency range. And the perfect absorption can be achieved when these two conditions are fulfilled. Now, the major part of this design is carried out using the numerical simulation. We use acoustic thermoacoustic interface of COMSOL to consider the thermoviscous losses in the narrow region. So here is the cross section of COMSOL model setup. We use the sound hard boundary at the interface of the structure and free space due to huge impedance mismatch. And also to capture the physics accurately, we use boundary layer mesh in the narrow regions. So once the COMSOL model is set up, then we optimize various geometrical parameters like height of the aperture, diameter and thickness of the perforated plate and all using the parametric sweep. So here are the optimized geometrical parameters, and for these parameters we generate the absorption coefficient spectra at 50 Hz. Then at this frequency we simulate the pressure profile. So we can see that as we go in deeper region, the acoustic pressure increases. So when the wave passes through this channel, it gets attenuated due to thermoviscous loss and get absorbed. For the acoustic absorption measurement, we fabricate the sample using 3D printer in our lab. First photo shows the internal view with the labyrinth structure, and second and third shows the horizontal and vertical view of the structure. For the experimental measurement, we use two microphone method. First, we fabricate a homemade waveguide to fix the sample at the end of the impedance tube. And here are the two microphones which are used to obtain the phase and amplitude of the pressure distribution. So after analyzing the signals from these two microphones, we can get the absorption coefficients. And here are the results that are obtained via all three approaches: experiments, theory and simulation. It shows the absorption spectra as a function of frequency. So we can see that for using all three approach, we get absorption at 50 Hz and also they matches very well. At this frequency, the total thickness of the structure is 13 mm, that is just lambda by 527, and the lateral dimension of the structure is 100 by 100 mm. Then we calculate the path length by calculating the mean distance from the zigzag, that is labyrinth structure, and from the cavity. So here the path length is 4.7, which is smaller than lambda by 4. It shows that this concept is not based on the quarter wavelength resonator, but it is based on the hybrid resonance. The hybrid resonance obtained via coil channel and labeling structure and Helmholtz type of resonance of the cavity. Further, for the bandwidth feature, we use supercell approach. So we connect a total 9 unit cell in 3x3 array. For each unit cell, we use different radius of the circular aperture. It means that each unit cell resonates at different frequency. Here, all the unit cells are combined in parallel, so their impedance can be calculated using this equation. As this structure is very large, the lateral dimensions are large, and we do not have facility to measure the acoustic impedance of such a large structure, so we consider theoretical and numerical approach. For the given frequency range, total bandwidth of 8.7% was achieved, and for this range, the absorption is more than 90%, but it could not reach to 1 due to a little impedance mismatch between the structure and the surrounding medium. So in the summary, how we proceed? First, we had the coiling up space structure, then we introduce a circular aperture and we get a frequency shift up to 92 Hz. Then after trying several geometries, we end up with a multiple structure, and using this, we get the absorption at 50 Hz. Now all this design process needs a lot of trial and error, and sometimes it is not possible for our human brain to think about such complex pattern. Specifically the non-intuitive design or irregular shapes that can also outperform the empirical structure. So for this, we implement the deep learning based approaches to design the non-intuitive metasurface absorbers. So now moving to the second part of the result, that is deep learning for acoustic metasurface absorber designs. Before going to how we have implemented the deep learning approach for the metasurface, first I will talk about artificial neural network in brief. So artificial neural network is inspired by the human brain activities. When we see some object, our brain tries to detect that object based on the information it has learned or it is saved. So this exact job is done by neural networks in our brain. So artificial neural network is nothing but an attempt to simulate the neural network of our brain via machines. So here is the approximation, and this model is basically a multi-layer perceptron network. The multi-layer perceptron network is a classical kind of the artificial neural network. Here, typical artificial neural network consists of several millions of neurons which can be represented by the circles, and all these neurons are connected in the series like this series of the layers. First layer to the neural network is input layer, from where we give the real world information, which is followed by several hidden layers. So the job of this hidden layer is to transform the information that it has received to in the way that the next unit can understand. The number of hidden layers depends on the complexity of the problem. And as the data goes from one unit to the next unit, the network learns more and more about the information. And at the output layer, network gives response to the input layer information. All the neural networks which are implemented in this presentation are based on the convolution type neural network. So they are simply extension of traditional multi-layer perceptron based on the shared weight architecture. This we can understand using example of this classical type artificial neural network. In case of convolution neural network, the hidden layers are made of the convolution layers, and what it does, it receives the information from the previous layer and then convolute them and then forward to the next layer. There are usually also non-convolution layer in this type of network, but these are the fundamental layer which makes it convolution neural network. The exact part of this network which helps to detect the object or information is known as filter. So there are various kind of filters. For example, in this picture, some filter may detect the edges, that is called edge detector. Then some filters may use to detect the shape of the structure, and then there are some filters which can detect the another information in the input. So now, how this deep learning can be useful for the acoustic designs. First, it uses nonlinear activation functions like sigmoid and ReLU, which helps to learn more complex structures. The second is data augmentation. Normally for the acoustic designs or physics design, we rely on the numerical simulation, especially in case of the non-intuitive design, to generate the training data set. And it is not possible to generate high quality and large data set by just performing the numerical simulation. So this data augmentation technique increase the quantity and diversity of the training data set by augmentation techniques like shifting, rotating, gamma transformation and many more. The next is multiple GPU. Most of the platform where we train the deep learning network allows to use us multiple GPU. So it reduces the training and inference time. Here the inference time is the time to predict the output by network once it is trained. Now for our case, we consider this kind of structure. So it consists of a perforated plate with a hole in the center. So in initial numerical simulation, we find that as the hole position moves towards the corner, we get the lower frequency shift. And in the back, it consists of a random shape of the propagation channel. This structure can be further represented in lattice structure of 48 cross 48. Here we divided the whole area inside this cavity into lattice of 2 mm square size. Here the lattice which are filled up with the dot indicates the area that is filled up with the PLA, and the lattice sides which are blank shows the area that is filled up with the air. For the initial simulation, I consider very small channel, then make it longer. So we can see that as the channel become longer, the absorption moves towards the lower frequency. Now to formulate the problem for the deep learning network, for example, we have this structure which we represent in lattice structure. Now this structure can be further represented into a pattern matrix like this. Here the matrix element is 0 if that area is filled up with air, and matrix element is 1 if that area or lattice site is filled up with PLA. So this is the input for the deep neural network, and we want the network to learn this function to find the relationship between different lattice sites, and in output we want to predict the absorption spectra. So first we implement the forward regression model. The idea is that in input we want to give the metasurface absorber, and in output we want the absorption spectra. So this is the input to the network which has shape 48 cross 48 cross 1 because it's 2D matrix. Then we forward this to the convolution neural network that consists of two pairs of convolution and the pooling layers. Here each pooling layer is followed by the ReLU nonlinear activation function. The output of the last pooling layer is fed to the flattened layer. Here the job of pooling layer is to reduce the spatial representation. It means that it reduces the amount of the parameter, and ultimately it reduces the computation burden during the training time. So After the last cooling layer, it is flattened into vector to fed into the fully connected layers. So here it is followed by two fully connected layers, and in output we generate the absorption spectra. For this model, we use 10,000 samples for the data set, and out of this we use 8,000 for the training purpose and reserve 2,000 for the testing purpose. The spectra of our interest is 30 to 70 Hz with a step size of 0.2 Hz. And here are the hyperparameters. These are the optimized value after the training. So hyperparameters in the neural network decides the network architecture. For example, how many convolution layer, cooling layer and dense layer we should use, and also for particular layers, how many strides, how many filters that we should use. And it also determines how the network is trained. For example, it determines various training parameters like learning rate, then what is the dropout rate, and how the weight is initialized to set the initial weights. So these are the optimized value of the hyperparameters. And here are the results. So this plot shows the spectral response for the three different structures that are representative case from the test data set. On the right axis, it shows the absolute difference between the simulated absorption coefficient, that is ground truth, and alpha p is the predicted absorption coefficients by the neural network, which is shown by green shaded area here. So for all these cases, we can see that simulation and prediction results match quite well, and for each cases, the mean square error is shown in the inset. For the last case, the full absorption is achieved at 38.6 Hz, where the thickness of the structure is 13 millimeter. That is just lambda by 684, and at this frequency the path length of the propagation channel length is lambda by 5.7, and this is the corresponding structure for this absorption plot. For the acoustic absorption measurement, our impedance tube is capable to measure the absorption above 50 Hz. So we simulate a structure with a little higher frequency to achieve the resonance at little higher frequency around 66 Hz. So here is the sample that is printed using the 3D printer, and it's the internal view that shows the complex channel. And these are the vertical horizontal and the vertical view of the structure. And here is the comparison of the absorption spectra obtained via the CNN and the experiment. And we can see that for both the cases we get the resonance frequency at 66 Hz. Further, to compare the accuracy of the implemented neural network, we compare it with three classical machine learning techniques: k-nearest neighbor, random forest, and support vector machine. So here we use the accuracy matrix, and we set a threshold of 10⁻⁻⁴ for the mean square error. So for the given number of sample, for how many sample a particular network can predict with the mean square error below this threshold value. For using this accuracy matrix, we can see that result the CNN has outperformed other classical machine learning techniques with the 86% accuracy. And here are the optimized parameters for all these machine learning techniques, which we optimize using the grid search method. So for the design that we saw now, the only variable was the propagation channel length, and the remaining geometrical parameters were constant, and it was only for the normal incidence. So in the next part, we design forward and inverse designs for omnidirectional incidence, and as compared to the previous design, this design allows more degree of freedom in terms of adjusting the geometrical parameters, and also it allows to simulate the predictions absorption spectra for the omnidirectional incidence. And here we use some advanced deep learning concept to make the robust network more robust for incoming variation of the data. Our percentage variance, and it helps us to reduce the dimension of the target absorption spectra from 201 to 20, that is 90% reduction. So after data pre-processing, first we implement the forward network architecture. Here this is the 3D structure, then we decompose in 2D pattern and 1D vector. Then we forward this information to the neural network. This convolution neural network consists of 3 convolution layers which are presented by C1, C2 and C3, and each convolution layer is followed by a max pooling layer M1, M2 and M3. Here the output of the last pooling layer is followed by the batch normalization process. This batch normalization process is used to train very deep neural network. So what it does, it standardizes the input to each layer using the mini weight size. And this way, it dramatically reduces the number of epochs to train the network. So this is the batch normalization, which is used to fasten the network, and we will see its effect in the next slide. Output of this batch normalization is followed by the flatten layer to flatten into vector. Then before feeding to the dense layer, dropout technique is implemented. Here what dropout do, it randomly drop out some neurons for each iteration. It means that for each iteration it generates slightly different network architecture, and at each time it also disconnect the forward and outgoing connection of the particular neuron that is dropout. So it is believed that this technique significantly makes the network more robust for the variation of the data, and it also reduces the overfitting issue. Output of this dropout is then fed to the dense layer. We use 2 dense layers, and at the output the absorption spectra is ready to evaluate. So this was the forward network architecture. And here are the training and absorption analysis results. This plot shows the learning curve as a function of epochs. The learning curves are training curve and validation curves. So epochs are the number which shows that to learn the network how many times we pass the data from it, and for the losses we use the mean square error function. Here alpha p is the predicted absorption coefficients by CNN, and the alpha s is the ground truth that are simulated one. We can see that as the training goes on, the loss is reduces, and after certain epochs, the training and validation curves become parallel to each other. It means that training is converged now. And here are the optimized hyperparameters after 500 epochs. Further, we carry out the absorption analysis. In deep learning, this absorption analysis is done to check the network performance, that if we remove a major part of network or we change the configuration, major configuration, how it affects. So we consider 3 cases: base model that we saw previously. The another model is without batch normalization process. Here it is shown by this black curve. So we can see that as compared to orange curve that shows the base model, this black curve converges a little later. So it shows the necessity of batch normalization technique in our network to reduce the number of epochs to train the network. And in the third case, we use the global average pooling layer instead of max pooling layer, but which is shown by the blue curve here. So we can see that it is highly unstable, and also the loss is very high. So it is not good to use the global average pooling layer. So this was the absorption analysis part, and here are the results after the training. So this plot shows the absorption spectra as a function of frequency for these two different samples. The first row shows the comparison of absorption for 0 degree, 30 degree and 60 degree incidence for this sample. And we can see for the each case, even for this sample too, for all 6 plots, we get the same absorption frequency for prediction by CNN and by the neural network. For each cases, here mean square error is listed. Here there is a slightly difference between simulated and predicted result. This can be further improved by increasing the data size. So once we implement the forward neural network, then we implement the inverse network architecture using conditional generative adversarial network, that is CGAN. Here the idea is that in input we want to give the pre-described absorption spectra at particular frequency, and in output we want to generate corresponding metasurface absorber structure. So we use CGAN, and this is the main architecture of the CGAN. It consists of main two parts, generator and discriminator. The generator receives the input from latent space and from the conditional information. Here the conditional informations are the acoustic response and the 1D vector with height and angle of incidence. So these are the input to the generator. Based on this information, it generates the images. And then the second unit of this network is discriminator. Here the inputs are the images which are actually fact, that is generated by the generator, and the actual images from the training data set. So during the training, this both generator and discriminator train alternatively, and they try to compete with each other. The job of this discriminator is to decide that whether it is coming from the generator and or whether the image is coming from the training data set. So based on this, the discriminator decides the real and fake probability. If the image is coming from generator, then it is considered as fake, so it's a 0 probability, and if it is coming from training data set, then it's 1 probability. So when it gives the probability 1, it means that discriminator is able to decide that it is actual output or it is fake output, and then this value goes back in back propagation to the generator. So based on this information, generator again set its weight and bias, and now it tries to generate more similar kind of information or similar kind of image from the training data set, and tries to make the discriminator full. So when this probability reach to 0.5, it means that now discriminator is not able to decide whether it is coming from generator or it is coming from the training data set, and then it is believed that network is converged. So in the detailed architecture, this generator and discriminator both are the convolution type neural network, and with a slight difference in their internal architecture. So here are the results. First row shows the samples from the training dataset, and the second row shows that samples that are generated by the CN. They all are quite similar, and here this black absorption curve shows for these particular structures from the training dataset. So once we generate the sample from the CGAN, we input it to console again to verify that what is the absorption response, which is shown here by the black red dashes. So for all these 3 cases, they match quite well with each other, and these are the hyperparameters optimized values. Okay, so in conclusion, in the first part, I talk about multi-coil metasurface. So we design this structure and achieve extreme low frequency absorption at 50 Hz with the thickness of lambda by 527, that is 13 millimeter. In the second part, we implement forward regression model that is 4 order of magnitude faster than the conventional FEM technique, and also we compare its output with other machine learning techniques, and this implemented CNN outperforms other with 86% accuracy. In the third part, we implement forward and inverse design for omnidirectional incidence. These network architectures allow to design the metasurface absorber with more degree of freedoms, and nearly using this kind of non-intuitive design and this approach, nearly omnidirectional absorption was achieved at 82 Hz with a thickness of lambda by 64. So here is the future perspective of this work. First is broadband acoustic metasurface absorber design for low oblique wave incidence. Till now, for the bandwidth feature, we use the supercell approach, and in that case, we connect many unit cells with different geometrical parameters. So it again increases the total size, and it actually kills the idea of acoustic metasurface. So it is essential to find some new principle for broadband acoustic metasurface absorber for oblique wave incidence for the low frequencies. The second is that this concept of non-intuitive design using the deep learning can also extend to the underwater sound absorption. And the third is progressive incorporation of state-of-the-art deep learning approaches. So we saw that it is extremely challenging in our case to generate the data set. Here we partially mitigate this issue using one technique, that is data augmentation. There is also one more technique, that is transfer learning, and deep learning community is time to time update and provides the new approach to train the model on the smaller data set. So this way, by incorporating with the state-of-the-art deep learning, we can also train our network and we can implement those approaches for acoustic metasurface design. And also there is one efficient way that to generate the data set, high quality and versatile data set, by combined effort of the acoustic community and put them on the open source platform like GitHub, so that everyone can use, and it then it can eliminate to generate the generate the data set process again and again for every metasurface designing, and it shorten the cycle of implementation for the network architectures. And this way, deep learning approach can accelerate the discovery and development of the advanced acoustic metasurface design devices. Thank you for your attention. Thank you.
Thank you very much for your presentation. It took exactly 45 minutes. So we will now ask a couple of questions, and we'll go in order of appearance of the committee members list.
Okay.
So we'll begin online, I assume,
Okay.
with Absorbing Acoustic, who is Director of Research at CNRS of University de Transfrontier. Not sure if
Yeah.
we can be heard.
Hello, Professor Kelly.
Yes, I can hear you. Good. Thank you very much, Mr. President, and I would like first to congratulate Mrs. Kirkpatrick for this scientific presentation of her work. Really, I found the manuscript well written and well structured in terms of results, so you can really go easily and see to get the most information directly from the source of the chapters. So that's been really, really good. I'd like also especially to point out that the state of the art was also really well described and even, I can say, a large overview of the domain, and not limited only to the, I can say, the absorption, but it covered, I can say, some also other properties of metasurfaces, which is really, really good. In general, I can say that you have two most contribution from your thesis to this field of metamaterials and metasurfaces. The first one is I can say, the continuation of the work of your group by introducing this multi-polar metasurfaces. So, in this system, you are extending the effective length of the resonators and get, I can say, an absorption at the very low frequency. The second one we presented in chapter 4 and 5. It's related to the deep learning, and this is like a really new approach for these metasurfaces that can be considered like powerful tools for designing practical metasurfaces for absorption of acoustic sound. So now, if I can say, I have some general questions. In chapter 3, when we present the multi-corridor channel, as in your presentation, you say that really what we need to consider is the real path of the wave inside all these channels. At the end, when you, the first question, because you have presented that the channel is close to lambda over 4, so a little bit, I can say, more performant than the quadrilateral blend. My question is, in this case, when you extend just the path, you are not changing the real, you are not breaking the rule of the resonators. We are usually close to the quadrilateral or Helmholtz resonators. We are not breaking the rules, because you say sometimes in your manuscript that you are breaking this. I don't think that it's very good way to say that you are breaking maybe some performance, because the way that you measure even the path can be a little bit different. So my question is how you measure the path of the wavelength in this kind of multi-corridor channels.
Okay, so here we measure the path after the end of the aperture, and by calculating the mean distance from all these 11 labyrinth structures and from the cavities between them. Yeah.
Especially usually in the corner, we have different possibilities to measure the path. So what is your strategy for the corner?
We measure the mean distance only for that cavities.
Okay. Now in the chapter 3, you do some technical question. In page 86, you introduce the RLC model for the multi-corridor channel. So my question, because in your system there is two things. There is you extend the path by introducing inside the channel.
Yes.
But also for the aperture, you are introducing like something that moves close to the Helmholtz resonator.
Yes.
Okay. So my question, what will be the difference between the model when you have the Helmholtz resonators, so the aperture, and the other one when you don't have this, just you don't have this extension of your system. Just
in the chapter 3?
You just find the name that you use in your. Yeah, we have like normal resonator or not. Is there any change in your model? In the RLC model exactly or not?
Can you please repeat? I could not understand it.
Yeah, I mean the circular aperture the circular aperture that you have between the perforated plate and your structure. Does it affect your RSA model?
Yes.
When exactly?
The question is between the system without aperture, how you modelize the aperture with the electrical model.
Okay, so we calculate for the third chapter, multi-coiled one, we embedded that aperture by calculating the acoustic reactance and the resistance provided by that. So we calculate using those equations and by considering the thermo-viscous losses in the third chapter.
Okay. Okay. Now, for the when you use your superset technique to augment the absorption, what I didn't understand, what is the mechanism that is behind? Is it like maybe ladder type filters, or you are constructing, you are manipulating, shifting the frequency from one set to another one to get this one, or a coupling, some mechanism of coupling between the systems? So what is the strategy behind this broadening the absorption?
So here, first we get absorption at 50 Hz with a particular value of the circular aperture. Then we tune this value of diameter of circular aperture so that we can generate the nearby resonant frequency with compared to this 50 Hz. And then by overlapping this resonance, we achieve the broadband performance.
Donc the company for this very nice talk. So I would like first to apologize because I didn't understand that you was a woman. So sorry for that thinking of the report, and I can redo also the report as well, but so sorry for that mistake. And also we'd like to thank Belredin for his invitation, for the participation of this PhD. So, as it is said by Abdelkrim, your PhD is separated definitely in two topics. The first one, which is more physics topic, with the absorption in the continuation of what is done in the team of Nancy. And the second part is mostly on the machine learning processes and so on. So of course, I'm a physicist, so I'm familiar with the first one, but I will ask you also some questions about this machine learning to see what we can find behind this kind of studies. So I appreciate your talk also. It was pedagogical also for this last second part, for me at least. And then it's also a nice representation of your work and a good illustration of the manuscript with some choices, because it's a little bit more deep in the manuscript. So the presentation is of the objective is clear, and the way to reach the objective is also clearly written in the manuscript. So we start with the introduction of this ultra-thin acoustic absorbers. On the manuscript, you talk about a single or hybrid resonant system. So what you have in mind between the two definitions of that, so the single and hybrid?
Okay, so the single resonant systems is based on the resonance only one type of resonance provided by structure like ampoules, but for some kind of metasurface, like I discussed that membrane type metasurface, the resonance provided by two different parts of the structure is different. So by combining that effect, we get the resonance is hybrid resonance.
Okay, so I mean that in the calling up, you are in the hybrid system.
So there are two types of resonance. The multi-coiled one. So it is based on the coiling channel first, and the another is labyrinth, and the second is Helmholtz type resonator that is provided by the cavity between those two labyrinth structures.
Okay, I see.
Ms. Krupalidonda, the jury has deliberated, we have discussed your work, and we have come to some conclusions. First of all, we all found that we appreciated the fact that you covered several topics, two particulars, physical acoustics and deep learning. Apart from your thesis, we also enjoyed your presentation, which was clear, pedagogical, well structured according to your thesis. You selected interesting topics that enabled the members of your committee here, the members of the jury, to better understand what you studied and what you investigated. So we've come to the conclusion that you get the degree of Docteur de l'Université de Lorraine. Congratulations.
Thank you very much.
So now it's time for you to say a few words. New presentation?
No, we don't.
For the training.
Okay, so thank you very much, Mr. President, for this. And first, I would like to special thank you, my professor, my supervisor, Professor Badreddin, for first for selecting me to work for this project and continuous support for all these 3 years. Not only the subject knowledge, I have also gained some skill like professional discipline and planning to execute the long-term strategies and all, which will be very helpful for my long-term career. And it was very nice 3 years to work in this group for Note 7. And then I would like to extend my thanks to all the jury members for reviewing my thesis, for your valuable suggestions on my work, that I will work on my manuscript based on this suggestion. Thank you very much for being here to attend my PhD defense. Then I would extend my special thanks to Dr. Yifan Zhu. He is not here, but yeah, I will send him the video that from the very beginning of this project, he has been very supportive for my experiment and numerical simulation work. Then I would like to extend my thanks to Professor Aurelian for fruitful discussions we have. It gives the deep insight of physics. And Professor Brice, he is not here. Yeah, I had less chance to interact with them, but I have a suggestion in initial days of my PhD from his side. So thank you. And then I would like to thank each and every one of my team for Note 7. And it's always been one stream to work with such a kind and hardworking colleagues. And thank you for all the support. Thank you very much, Shan, Liu, Shivan is not here. To my senior, Steven, he also motivates me. And my junior, Tong and Manix. So it was a very good 3 years in Nancy with all the friends outside my team. Thank you very much. And also for Hardik for coming from India to attend my PhD defense. And thank you to my family also. Thank you.
Il lui reste, je crois, 6 mois. Donc je sais pas comment ça se passe.
I shall be here.